So, hello everyone. My name is Dominik, and I'll be presenting some joint work with Azadeh. Maybe many of you have seen her keynote this morning, and my advisor, Andreas Podelski. And if you've seen the keynote, you'll recognize some things, right? So we also work in this field of commutativity reasoning for verification. And in this work, we have extended it to parameterized programs. That is, programs with an unbounded number of threads. The main observation is already the title, namely, in this context, also commutativity simplifies the proofs. And in the next 15 minutes, I'll explain to you in a bit more detail what exactly that means, and I'll give an overview over the detailed contributions that you'll find in the paper. So we start with the object that we study. Parameterized programs, as I said, are a formalism for concurrent programs. We are given a thread template, just a single template, here given as a control flow graph. That control flow graph uses a number of variables, some global variables that are shared between all thread instances, and some local variables that are local to each instance. And the parameter that is responsible for the name parameterized programs is the number of threads, which in this talk I will call n. So that means that for any value of n, I can instantiate the program. I get an instance p of n by taking n copies of the thread template. I'm going to do some renaming of the local variables so that they can be distinguished, and I will take the parallel composition of those n copies. And the verification problem that we are interested in is to show that p of n is correct for any number of threads n. So we want to show this correctness in one verification run for all n. Correct here means safety properties, particularly let's assume that the thread template contains some assert statements that we want to never be violated. So to just make this super concrete, a very, very simple example that we'll see throughout this talk. We have a thread template, a control flow graph with two locations, and each thread, therefore, alternatingly increments some variable x and decrements it again. X is a global variable. In this example, we don't need local variables. And the specification that's part of the thread template says whenever some thread is in this location L plus here, then x should not be 0. And this should be always the case when the thread is here. So even if some other thread then decrements x, we need to prove that x is still non-zero. We assume that x is initially 0, so that this actually holds. So if you think about this for a few seconds, you can probably convince yourself that this is indeed a correct program. But we'll see that if we want to prove this, and prove this in an automated fashion, we're already encountering some challenges, even though this is such a simple program. Yeah, so let's look into that. How would we verify a program? Well, we'll of course start by looking for an inductive invariant, as we often do. And when we talk about the inductive invariant for a parameterized program, we mean one invariant which is inductive for any number of threads n again, right? So again, we have this challenge that we want to cover any number of threads. So here, this means this invariant must talk about the local states of an unbounded number of threads, because we don't know the number n, and that means we have an unbounded number of local variables. So to make that somehow tractable, one often looks at a specific kind of invariants, namely thread modular invariants. Those are simply invariants that start by quantifying over all thread IDs, so for all thread IDs from 1 to n. And then we have an assertion here at the end that talks only about the local variables of the thread instance I, the global variables, and possibly the location of the thread instance. And through this quantification, we can talk about these unboundedly many variables. And that's very nice and intuitive. The only problem is, in general, that's incomplete. We will find programs for which no thread modular invariant exists, even though they are correct. There is a standard solution for that in the literature, and that is to introduce some ghost state. So we're going to introduce some fresh ghost variables into the program that are updated at certain points, but they're not actually used by the main computation. We only use them in the invariant to relate them to the actual program variables. And typically, we use them to record some information about the computation that has happened. This is very nice. It gives us a complete method, but for automated verification, we still have some challenges. Namely that, what kind of ghost variables could we look at? We could design them ourselves, tailored to the program and property we want to prove, but if you're an engineer, verification engineer, that's nice. If we want to automatically do this, this is very difficult to synthesize. There are approaches for it, but it's still a big challenge. There are some canonical definitions, so a history variable would record basically every step of the computation, but if you want to express something meaningful about the history, you very quickly end up with some undecidable logic, and then for automated verification, that's again a problem. Or you could look at the local state of some other threads. You could represent that through some ghost variables. If you had only a fixed number of threads, that would already be complete. But in the case that you have an unbounded number of threads, as long as you look only at finitely many other threads, you're still incomplete. So this picture is quite unsatisfying for automated verification. We still can't prove many programs. And this we'll see in our example even. Right, so even though this was a very simple example, let's look at all the traces that this program could execute. Well, it's the union over all the traces of all the different instances for different numbers of threads. And these traces look very different, right? So here we have different colors, meaning different thread instances, and we have wild interleavings between them. There are some increments by the first thread in yellow, but in the middle there could be some increment by the second thread in green. There could appear a third thread that increments and only decrements much, much later, and so on. You have a lot of possibilities, as you can imagine. And the result of this is that it's very difficult to give a proof for this. In fact, there is no thread modular proof for this program if you don't have ghost state. Right? Basically, the problem is you want to say something about x, this variable that's incremented and decremented, but unless you know what all the other threads have done, whether they have incremented or decremented or both, you can't say anything meaningful. And yeah, this is where our solution comes in. We are going to use commutativity. So I'm just going to very quickly reiterate what commutativity means. This is this observation that for many statements of different threads, the order in which you execute them doesn't actually matter, and then we say these statements commute. So for instance, in our example, whether I first increment thread x in thread 1, and then decrement it in thread 2, or I do it in the opposite order, doesn't make a difference. The effect in both cases is that x in the end has the same value as in the beginning. And therefore we can say that traces, this gives us an equivalence between program traces, going back to Marcinkiewicz, where we say traces are equivalent if they only differ in the order of commuting statements. The key property that is maintained by this commutativity is that if one trace is correct, all the equivalent traces that only differ in this order of commuting statements are also correct. And this enables this key proof rule that you can take a reduction, which is a subset of traces which has one representative for each equivalence class. And if you have shown correctness of the reduction using some invariant, then you can implicitly conclude that the entire program is correct, even if your invariant is not actually inductive for the entire program. And let's do that in our example. Right, so what would a reduction of this program that we saw look like? As we saw in the previous slide, the increments and decrements commute freely against each other. 2 increments and 2 decrements also commute against each other. So we are very free in choosing our representatives. And one thing that we could do is choose only those representatives in which we first take all statements of the first thread in yellow, and only after the first thread has no more statements in our trace, we start taking some statements of the second thread in green, and if there's a third thread, it only starts its computation after the second thread has finished, and so on. So in this particular example, we in fact have basically a sequential program where we order all the threads one after the other. This isn't always the case that it's the sequential program, but the technique works in other cases as well. Now, what's the advantage of this? Well, now we can give a much, much simpler invariant. In fact, we can simply say that the invariant is, for all thread IDs, it holds that if the thread I is currently in its initial location, which was L-, then x is greater or equal to 0. This holds initially, so that's fine. Whereas if the thread is currently in the location L+, it has just executed the increment, then x is greater equal 1. And this was an inductive already for the previous program, but now this was an invariant of the original program, but now it's inductive, because if we're in L+, previously some other thread could decrement, and then we no longer know that x is greater equal 1. But now the only thing that can happen when we're in L+ is that either the thread I decrements, so we move to L- and x is greater equal 0, or if another thread now makes a step, it must be its very first step. And then the very first step is an increment, and we still know that x is greater equal 1 after the increment. All right, so through this reduction, we had a program with no thread modular proof, and now we have this very simple thread modular proof. What a wonderful observation. But how can we actually use that in a verification approach? Well, one first problem that you encounter when you want to do this, especially in an automated verification approach, is that you need to somehow represent this reduction. Right? Here it was an infinite set of traces. We were going to need some finite representation. And a very nice observation that we had is that you can actually represent your reduction again as a parameterized program. This is a bit surprising because the traces that we saw here, they look much more nicely ordered and not as chaotic as the traces of a parameterized program. But if we manage to do this, it has a big advantage, because now we can compute this reduction, represent it as a parameterized program, and any verification technique for parameterized programs can be applied on the result. The verification doesn't actually have to know about commutativity. I'll not show you the details, they are in the paper. We do this through a transformation of the thread template, so we're going to add some new variables to it and instrument the code. And the result is that in this instrumented program, the execution of any trace that would not be in the reduction will at some point block. Some guard will be violated, the guard uses the new variables, and therefore this trace cannot continue to execute. Let's make this practical. We, as a proof of concept, applied this using the verification technique of thread modular verification at many levels. This is a technique from POPL'17 for parameterized programs, and this technique has no idea about commutativity. It works through a translation to constrained horn clauses. We applied this on 19 benchmarks, parameterized programs, all of them correct, that we collected from the literature and added some custom ones. And I'll just give you the headline results. For the original programs, 4 of them could be proven with this technique. In 11 cases, the constrained horn clause solver actually determined that no thread modular proof exists. And in 4 cases, it timed out. With the reduced programs, we can now prove 14 of them, so a significant increase in the expressivity. In none of our benchmarks, we actually determined that no thread modular proof exists. And with that, I'll come to the conclusion. So just to summarize the contributions, we extended commutativity-based reductions to parameterized programs through an encoding of the reductions as parameterized programs by transforming the thread template. In the paper, you'll also find a discussion of different reductions, different choices of representatives for a program. This is important because different reductions often enable different simplifications, so you want a lot of choice here. We then characterize in more detail the kind of ghost state simplification that you can and cannot achieve through this. For that, we use the framework of Ashcroft invariants. So these are thread modular proof where you fix as ghost state that you look at a bounded number of other threads, and that allows you to nicely characterize the simplification. We applied this in thread modular verification at many levels, and because this translation to constrained horn clauses, with the reduction, it gains a lot of expressivity, but you have some performance issues. And we showed that through a kind of symmetry reduction on this encoding, you can significantly improve the performance of the CHC solvers on the translation. And with that, I am finished, and I would be happy to answer your questions.
Thank you very much. Let's get to the questions immediately.
Thank you for the very interesting talk. I had a question about the commutativity relation. Thinking about fixed size integers, for example, when you have 32 bits, and it's still true that you can swap plus and minus operation, because you could reach integer overflow error. So did you take into consideration these kinds of memory models, these kind of situations?
Yeah, so we take this into account. In some cases, you could still convert this, right? If your integers wrap around nicely, then plus and minus still commute. In our implementation, we encode this as an SMT formula, and we ask an SMT solver to determine if things commute or not.
Okay, makes sense. Okay. Thank you.
Hello. So thank you for the nice talk. So I have a very technical question, which is, I guess you're again doing the same tree automata LTA business under the hood for reductions. What happens to the alphabet? I mean, when you have infinitely many threads, then the alphabet becomes, so how do you encode this?
So here we are not directly working with the automata. We're really applying the transformation on the thread template, on the code, so to speak, and then we are translating this to constrained horn clauses. And then it depends up to the constrained horn clause solver how that is solved. So we're not working.
So you're not looking for all possible reductions?
No, here we're fixing a reduction, right?
Okay.
So we have a parameter of our construction. These pairwise preference orders gives you different reductions, but in one verification run, we fix the reduction.
Thank you.
Thank you.
Thank you. That's a really elegant proof. The example you've given as motivation is kind of one that seems to fit nicely with kind of counter abstraction. So are all the ones that you've got to work better here ones that fit with counter abstraction, or is there sort of something else sort of as a good example?
Yeah, that's a nice observation. In this example, indeed, you might just do it with a counter, but this is not always the case. So we have a motivating example in the paper where you're talking about some kind of queue of messages, and that you cannot capture with a counter, but you can simplify the proof with this technique.
Another one here.
Just a very quick question. I was wondering, like, I guess your reduction doesn't really depend on the data types, right? I mean, you have like, by some chance you have integers here, but I guess if you talk about CHC, then you can go to any kind of local whatever data types, no?
Yeah, in principle that should work similarly.
We have got 2 minutes, so other questions? I have got one. I'm not clear. Can you the threads have loop inside them, and can you have different threads rather than many copies of the same thread?
We can have loops, right? We're looking for an inductive invariant, and that would, if we find one, we can prove that the program is correct no matter the number of iterations, so that works. In our tool, we also support a number of different templates. So we have a slide extension where you can have a finite number of templates, and you can also have some threads that you only instantiate once if you want a server and an unbounded number of clients, for instance.
Last question, and please swap the laptop, but don't take the microphone yet.
If I saw correctly, you have one example in which you timed out, one more example that you timed out, right? Do you have any insight to why that happened?
Yeah, that's actually a good observation. It turns out this constrained horn clause encoding, with all the additional variables that you add, it doesn't always make the solvers faster. So there's actually one program that we can prove without the reduction, and then there also should exist a proof with the reduction, but the constrained horn clause solver just gets confused by the extra variables and times out.
Thank you, Dominik.
Thank you.